Greetings everyone to this little resource overview of replicating the interpretability in the wild paper. So this is a Google Colab that Neil Nanda also made from his transformer lens examples. And if we click here and just go to the Google Colab, and the Google Colab is of course just a way to combine text, code, and the outputs of that code in a very useful fashion. So this has the setup and introduction to the problem itself, the direct logit attribution, so analyzing how the circuits look by looking at how at which parts of the model contribute to the output, to the correct output specifically. Activation patching, making this like intervention on the model so we can figure out what areas of the model are related or have causal influence on the correct output. And then visualizing the attention patterns and so on and comparing them to the paper. So in the beginning there's this setup, and here is a lot of stuff. And this is covered in the other video, what those mean, so I won't explain it here. And it's a demo notebook for the Transformer Lens library, which of course is the newer version here, version 1.0, formerly known as the Easy Transformer library, which is a library for mechanistic interpretability research on GPT models. Yes. So in this case, indirect object identification is basically looking at the task after John and Mary went to the shop. John gave a bottle of milk too, and then the answer should be Mary, right? Because John is giving the milk to someone, so it won't be John, it will be Mary. That will end the sentence. And this task is called indirect object identification, figuring out that it's actually Mary and not John that you want to end the sentence with, and we can sort of find a pretty direct algorithm for this. And here we set up the transformer using the transformer lens library. So we take the GPT-2 small here, and we verify that it can actually do the task. So after John and Mary went to the store, John gave a bottle of milk too, and the answer should be Mary, right? So we see that this probability is very high that it will be Mary. So it can actually do the task, which is always good to just check. So make sure you do that. And now we can find some reference prompts to run the model on. This basically just generates a small data set of different versions. So when John and Mary went to the shop, X gave the bag to, and this will be replaced with John and Mary. And when Tom and James went to the park, Tom gave the ball to James, and so on and so on. So these are just a few different examples, so we make sure that it's not just a too specific effect to some degree. Yeah. We now run the model on these prompts and use the run with cache. And what this function does is that it enables us to save all of the activations. And let's see, we probably forgot to run this one. There we are. We probably forgot to run something. Let me just pause and see. All right, so as you can see, it does say there's no GPUs available. So that's because I have to change the runtime, and you might hit this problem even earlier actually. But I'll change the runtime from none to a GPU. And I'll just say standard, I don't need anything there. And then I will rerun the code until here. So I'll pause again. And yes, delete previous runtime because we're doing a new one now. All right, so we have now rerun all the fields with GPU enabled. So now this can work. And we'll basically go ahead and we'll check if, how the performance looks on the correct versus incorrect token upon performing various interventions. So that'll be our metric. And so we'll just create this this hook that'll work to calculate this. Here we are. So average logit difference is this much. And yeah, it clearly works to give apparently a 33 times higher probability on the correct answer, which is pretty good when we haven't done any interventions yet. And I'll go through this because it's useful for your own mechanistic interpretability projects, but doesn't necessarily have much to do with actually replicating the paper. But we can pretend like we're going through the same reasoning process that the authors did when they were going to write the paper, and brainstorm what's actually going on. So this is obviously not too optional for you if you're running your own experiment, but in this case it is optional. And what we see is that our hypotheses will help us really on what we want to do, and if we don't have any hypotheses at all, we can get a lot of data and not know what to do with it. And if we are overconfident in an incorrect hypothesis, we can be unwilling to let it go and, see when reality actually contradicts you. And there is so spend some time thinking through how you might imagine this behavior. And his own reasoning, I'll also just go through that. So when John and Mary went to the shops, John gave the bag to Mary. So it's like here he also thinks through, if a tiny model could do this, like thinks through what are the specific architectures of transformers, how do they work. So a one-layer attention-only model probably could not do it. As he says, pretty sure the answer is no, because it's very good at primitive operations or copying information. So John to John, it could do that, but it couldn't actually do something advanced like writing Mary instead of John due to some previous information because of some technical aspects. And here it's useful to know more about transformer models, but of course you can run these tests without necessarily knowing much more than that. And so he comes up with two natural ways that it does this. One is that it detects all preceding names, so Mary, John, John, and moves this information to 2, and then deletes any name corresponding to the duplicate token feature. And so this probably happens in an MLP layer because of the nonlinearity and so on. And the second one is what is actually happening, which is that you have a head which attends to all the previous names, but where the duplicate token features inhibit it from attending to specific names. So it'll only attend to Mary, which means that the output will then map into the logits there. And then you can create an experiment where we are blading some stuff and so on. But let's jump into direct logic attribution. So this is a way of looking at which parts of a model contribute to the probability being high on this specific output token. So this is pretty useful, and I believe it is from a specific paper. Alright, yes, it's definitely from a specific paper, but maybe not the one I was thinking about. But you can see some context in a mathematical framework for transformer circuits, which Nanda was also a co-author on. And you get this output logit, which is equivalent to projecting onto a direction in the residual stream, as is written here. So you do this model tokens to residual directions to map the answer tokens to that direction, and then convert it to logit difference directions for each batch, because you can like reverse engineer what has happened throughout the model to some degree. Yeah, and then we get out these logit difference direction shape and the answer residual direction shape. And we can verify that this works by just applying this to the final residual stream for the cached prompts and verifying that we get the same answer. So you can see calculated average logit difference and the actual logit difference, which is the same. So that is correct. And now we can use a method a technique called the logit lens, which there is a link here. I'll just click. And this details it a bit more. Interpreting GPT, the logit lens, quite a good post. And this is just a way to interpret how it works. And this looks at the residual stream after each layer and calculates the logit difference from that. So it simulates what happens if we delete all the subsequent layers. And we see that when we do this, the model is completely unable to do the task until layer 7. So you can see it's all the way over here. Mid 7, it begins actually being able to do the task at all. So this is quite fascinating because it might need some quite advanced functioning or quite advanced algorithm that it only learns if it has complex enough prior reasoning or something along those lines. And a fascinating point is also that the performance decreases afterwards. So this is quite interesting. So we can see that, we can see how much does a layer contribute to the good logits we want, and then do that for all layers. And this layer attribution, we can then repeat the analysis for each layer. So looking at these adjacent residual streams, and this can then show us, okay, where do we have negative impact? And this is quite useful. So here we can see that layer 10 and 11 actually have negative impacts on the task being performed well, while 9 is having a great time doing what it does best, help us. And these are called like negative name movers. And there's a bit more reasoning in the paper itself, interpretability in the wild again, about why this might happen. Some thoughts on that. And now, we have a layer that is clearly quite interesting, but can we further break this down into an analysis of the heads, so decomposing attention output into the sums per head. And here we can then see that, again, layer 9 clearly has a very positive attribution, while layer 10 has this one that makes it, makes the logic even worse on Mary, even though that's the correct token output. So layer 9 is really carrying the load here, which is wonderful. And the attention heads are very good to study because we can look at their visualize the attention patterns themselves and see what they attend to. And if we just inspect the patterns down here, let us run it, we can see that the top 3 positive logic attribution heads, they are running. And maybe I will just pause here and then wait until it is done running. Perfect, that just took a few seconds. And then we can see what are the 3 heads, so layer 9, head 9, layer 9, head 6, and layer 10, head 0, that contribute the most to it being correct. So if I click here on this one, then I hover over 2, then you'll see that it looks a lot at Mary, because it's like, okay, what will come next now? And for the other head, again, it looks a lot at Mary. For the next head, it looks a bit at Mary and a lot at end of text. So that makes sense. And here are the negative ones. So if I say 2, then it creates a negative pattern on Mary, which is the negative name mover heads, which seems a bit interesting, seems a bit weird, but makes sense. So they all attend to the same word Mary, but they have different functioning. So this is layer 10, head 7, and layer 11, head 10, and layer 11, head 2. Yes, and now we only look at the very end of the circuit with these with the methods we've shown until now, and these are the parts that directly affect the logic itself. But here, if we use the method called activation patching, which can also be called causal tracing from the Rome paper, so rank 1 model editing from David Bauer and Kevin Meng, we can basically patch the activation, ablate it, so replace it by some other activation, and then see, okay, did this part of the activation actually affect the output, or do we find some big logic difference between this part being ablated versus this part not being ablated? And then you can figure out which parts are the most important. So here we run it into the residual stream, and we get, these are the corrupted tokens. So we'll assume that Mary gave the bag to John and John gave the bag to Mary. That we'll get some corrupted output. And we intervene on the corrupted run and patch in these clean residual stream at specific layers and positions. And we use this hook point feature from the transformer lens. And from this we can show that it is only at layer 8, so layer 9 in this case, our hook is before layer 9, so it is actually, this is a representation of layer 8's, the difference you get from these residual streams. So until then it's just looking at John, but then here it's looking at, it's actually moving the information from John to 2. Yes. And we apply this same idea to the attention or the MLP layers instead of the residual stream. So they have identical shapes, so we can reuse the same hooks, which we created further up. And you can read through all this if you're more technically inclined and edit it and so on as you want. And we can see that there are several attention layers that are significant. And the activation is extremely localized. So you can see layer 9 is positive. Here we are, layer 9, while layer 10 and 11 are very negative towards giving the right output. And the MLP layers don't seem to matter much. This makes sense. So our first hypothesis up there from the beginning is sort of disproven a bit, that it's clearly not the MLPs that matter that much. And this he mentions here that the one exception is that MLP stands for multi-layer perceptron, but the MLP layer 1, layer 0, which matters a lot, but this is probably just misleading and probably a generally true statement instead of about the specific algorithms. And we refine the above analysis then by looking at individual heads. So we loop through the heads themselves. So for layer in range model layers, for head index, and then we run these patch logits on top of it. We run the corrupted tokens, patch logit difference, patch head, cdiff. And from here we get all these values for specific heads. How much do we see that they contribute to the actual output being correct, even when we have done activation patching? Yes. So this is patched head output, and we can see that again this corresponds to layer 9 a bit here. Let's see. Yeah, it seems like there's some interesting heads that matter a lot that might be involved in detecting duplicated tokens as well. And then we can decompose the attention layers into these patchings of individual heads and decompose the heads into some semi-independent operations. So where to move the operation and calculating what information to move. So this is something we can plot as a heat map, and it's apparently hard to interpret, which I believe. So we can interpret it better if we use a scatter plot. And in this case, we can see that the early heads, they don't matter that much. So the earlier heads and late name movers don't matter at all now, while the mid-late heads do. So plot things a lot is sort of the lesson. Yeah, you can see layer 5, layer 9, and then these that matter a lot. The mid-late ones compared to the early ones and the late ones. Yes. And then we can see the opposite effect if we patch in the attention patterns, that the early and late heads matter a lot. So basically this is, information moving. So who's most relevant there? And we basically see specific heads being more relevant than others. So here, and there's apparently a couple out here that are very negative. So that's again layer 10 and layer 11 that does some weird negative head mover things. So it moves the information with a negative effect. And so now we zoom out and we consolidate our understanding, as it says. So we find that that these early heads, they matter a lot on the second subject, and they're determined by the attention patterns. These mid-late heads that we looked at matters on the final token, and their behavior is determined by their value vectors, so that's what we're moving. And the late heads, whose output matters on the final token, and their behavior is determined by their attention pattern as well. So here we can then imagine that both the early and late detect. So an actual speculation is that early heads detect both that the second subject is repeated token and which is repeated, so the John token is repeated. The middle heads compose with this and move this duplicated token information from the second subject token to the final token, and the late heads compose with this to inhibit their attention to the duplicated token, and then attend to the correct indirect object name and copy that directly to the logits. And now we can then visualize the attention patterns, so we can validate this by looking at the attention pattern of these heads. So we take the top 10 heads by output patching in absolute value and split it into early, middle, and late. And these middle heads attend from the final token to the second subject. Late heads attend from the final token to the indirect object. And one early head attends from the second subject to its first copy, while the other two mysteriously attend to the word after the first copy. So let's see here. Here we have the top early heads. So if we say 2, John. Yeah, so this is one of the ones that look at the word after John. This again looks at a word after John, and this actually looks at John when we click on John. We have the top and middle heads. So here, if we click here, we'll click on 2, and it looks at John, which is the duplicated name. So there's clearly some information on this being a duplicate. And here there's one who also looks at the next word a bit. And here again, these ones looked at Mary, and their attention patterns, so they are name mover heads, right? And we can now refer to the far more rigorous analysis in the paper to compare the results. So this is the sort of the circuit they find within the neural network. So you have the previous token heads, 2, 2, and 4, 11. The duplicate token heads, layer 0, head 1, 3, 0, 0, 10. Induction heads, so they copy, right? And the inhibition heads, so they avoid that we like it inhibits the wrong name. And then you have these negative name mover heads that we also found in the 10 and 11 layers. The name mover heads that we found in these in the late layers, and then the backup name mover heads, which is something the paper only looks at, but we haven't in this specific Colab, which is basically that these heads only activate as name mover heads if we ablate or remove the name mover heads themselves. Yes. So we did fairly well. Definitely not perfect, but these are some fairly generic techniques and some a priori reasoning, so it's pretty cool. And you can see Neil digs a bit, or breaks down the categories again, the early, middle, and late. So these are name movers, the late ones, and let us go out of that. The middle are the S inhibition heads. They copy the information about the duplicate token, so this is that it is duplicated itself, and these serve the purpose of detecting that there is a duplicate token itself. And there's some more information here, and you're very welcome to look deeper into it and run more and, get inspired for your own project. But otherwise, I'll leave it up to you to look at the rest. Let us just check out what there is compared to the paper. Bonus, early heads and induction heads. Interesting stuff. But good luck with your project, and we're excited to see what you come up with. Hey.